Well, yeah, I could do that. There's all kinds of stuff going on. If you're in Professor Brown's class, you might notice he hasn't been here. He's not going to be here this week. He's still in Italy. I left him there.
And did he complain?
He has not complained. Well, actually, he has. He complains about things, you know, but I don't listen when he complains about that sort of thing. So the integration of the CubeSats and the Pocket Cubes went well last week. So we were at the National Council for Research outside of Rome, and we integrated Bob's 2 Pocket Cubes and a variety of other small satellites. And so that was very successful, so very exciting. What else? It is scheduled still for launch on November 21st out of Yasny, Russia. So that's exciting. The interesting thing, though, at about the same time, Kentucky Sat 2 will also launch. Its launch slipped. It was supposed to be November 4th nominally, I believe. But because of the sequester and the federal government shutdown and that sort of thing, the launch has now slipped to, guess when, November 19th. So that's good news. Yeah. The bad news is we have 2 launches from 2 different continents within 2 days of each other now. So I'm not quite sure exactly how we'll handle that. It'll be really interesting for LEOP. You guys know what LEOP is? Launch and early operations. Because of when the satellites launch, there's a few frantic weeks, days, weeks, trying to figure out months, trying to figure out, number one, which is your satellite in these cluster launches, and number 2, trying to make the first contact. It's non-trivial. So now we may have 2 LEOP missions at the same time, which will make life really interesting in around Thanksgiving. So we really need to get you guys up to speed on both the UHF amateur radio Yagi dish antennas, and also train a couple of you up on the big 21 meter to schedule passes. To transmit, you have to have a license. You can pull down data and telemetry without a license. But you guys that are all in DC circuits, right? I guarantee you could pass the amateur radio. Which exam is it? The first exam? They call the technician exam.
You want to get the technician.
But I tell you, with just looking at the question set for 30 minutes on the internet, plus your knowledge that you've already developed in DC circuits, you could do it. I mean, really, you could do it. It's Ohm's law. I mean, well, that's one of the. There's a lot of. Trust me, you spend 30 minutes studying for that exam. Then you'll be able to transmit and command anybody's satellite that
Dave, what's your comment?
that you want to. Yeah, Will, you had a comment?
Oh, I was curious, what is the delay after the satellite launches on Kentucky Sat 2 before they're allowed to push them out?
Okay, so there is a primary payload on the Kentucky Sat 2 mission, and there are 33 CubeSats, I believe, on this mission. And so there's a sequence. So there is once the primary satellite's been deployed and it's happy and safe, and we don't quite know what that interval is, then they go through the sequence of ejecting all the satellites from the P-pods. And with that many P-pods, 11 P-pods, I'm not quite sure where we are in the lineup. So, and then there's a 45-minute RF inhibit period even after deployment. So it'll be, within an hour. So there's launch, and how long does it take to get to orbit, to LEO? 10 minutes, 12 minutes, right? So then you got a deployment sequence, probably over an orbit-ish. So that's another hour, and then a 45-minute inhibit. So within 2 hours, of the actual launch, we should be able to attempt to contact the satellite.
So it's not like the 18-day waiting?
Not like that. And the 18-day waiting period on the Italian satellite is still in debate. We're pushing for a 45-minute inhibit period. The Italians want an 18-day inhibit period, so we're it's very interesting negotiating with the Italians. You guys will learn how to do that. You're going to learn so much in this program. Technical information, cultural information, how to negotiate with other cultures. Yeah, how to use hand gestures. But yeah, so we don't know. We're trying to compromise on the ejection period. With a longer flight, here's the concern with waiting 18 days. How many days and it's a 98-degree inclination, and that's, by the way, this is probably a good segue for the discussion today, talking about orbital mechanics. It's almost a polar orbit, essentially, right? So you're flying through the horns of the poles. You guys have talked about radiation effects a little bit so far. So you're flying through both poles, and guess what? The South Atlantic anomaly on just about every orbit. So you're orbiting the Earth every 90, 100 minutes, and you're flying through those 3 danger zones every single orbit. So how many opportunities are there for single event upsets, for latch ups, for basically just toasting your electronics? So the longer it goes, then the higher the probability is that the command and data handling system could not initiate the ejection sequence. So we want to get out as quick as we can, because we don't want the Italian satellite to be subjected to all those hazards before we get out. Yes, ma'am. That's a good question. Don't know the answer, really. Yeah. Yeah, it's a good question. We haven't heard a reasonable argument why the 18-day period was selected. So.
Did the Russians not ask for it?
The Russians asked for a separation period between the primary satellites and the secondary payloads like Unisat 5, but I don't think they need 18 days. I mean, they'd be happy with. I mean, So the way that the Dnepr works is there's a lower stage, and this is such a cool rocket. I'll tell you just a little bit about it. So it's an old ICBM, right, called the SS-18. So what a beautiful philosophical idea, because this thing, all these ICBMs, SS-18s, the U.S. Department of Defense refer to them as the Satan missile, if that tells you anything about how deadly they are. They had nuclear warheads on them, and there were hundreds of them, maybe thousands of them, all throughout Russia and Kazakhstan. Nuclear warheads, and guess who they were pointed at? Yeah, so, pardon me. Call from space. It's just NASA, we'll call back later. So, okay, so there is this détente treaty, basically, that comes in negotiated between the U.S. and Russia in the 80s, and the idea is to reduce the world's nuclear arsenal and make it safe, a safer place for everybody. Well, that's great. So we destroyed a bunch of our ICBMs. They destroyed some of their ICBMs. A lot of the nuclear warheads were removed and hopefully in storage somewhere. So along comes this Russian company called the Cosmotros, and they offer to basically take over all the old ICBMs and convert them into launch vehicles for paying customers. So they negotiate a relationship with the Russian government through the Roscosmotros and the Ukrainian government, because a lot of the silos are in the Ukraine, they're in Russia, and they're in Kazakhstan. And the idea is to go in and reprogram the navigation system. So rather than making an Earth intersecting trajectory, they actually put satellites in LEO, and then they can sell the payload capacity. So the entire world's community of satellite developers gets inexpensive access to space. Under the treaty, the détente treaty, they have to get rid of these missiles anyway, so they're actually meeting their obligation to détente. And guess what? We have one less nuclear warhead pointed at us. So what an incredibly nice philosophical process that is. So anyway, the Dnepr is just an amazing rocket. So the way they work is they have this spacehead module, they call it essentially. And so just tell you a little bit more about the rocket. So it's a silo launch rocket, right? So what it has is a pyrotechnic steam explosive in the bottom of the silo, right? So it sets off this charge that creates an enormous steam explosion, and the pressure from the steam pushes the missile up above the door of the silo, and it just hangs there in space for a second. Then they ignite the first stage, and then it just takes off. So I mean, it's a bizarre to see it because you see all the steam coming out of the silo. Then the rocket gets up a little bit, but it has no ignition. There's no main engine cut on until you're literally out of the silo, right? So then it hangs there just for a second, then it takes off. Then there's a second stage, and then there's the spacehead module, which separates from the upper stage, and then it can actually maneuver any way it wants to in space. So it gets to the desired orbit, and then it launches the primary payload and the secondary payload, and then the other expensive customers, and then ultimately us. So it has incredible capabilities to put satellites into very, very specific orbits, and it can take a variety of payloads up. So it's just an amazing vehicle. So we got the launch out of Wallops on the 19th currently, and the launch out of Yasny on the 21st. So lots of neat things going on here. So moral of this story is please learn how to use the ground stations, whether or not it's the Yagi array or the big dish, because we're going to need lots of help with establishing contact with various satellites. And because we got the big dish, everybody else wants us to try to contact their satellite too, because we got a lot better shot at it with the high gain dish. So anyway, in all your spare time, when you get tired of studying for physics exams or calculus, please come and learn how to use the antennas. Okay? All right. So that's a little bit of a primer. Let me jump into the topic for today is satellite orbits and orbital mechanics. Usually this takes about 4 days to give you an introduction to this topic, and apparently I have about an hour and a half to do it in. So I'm going to breeze through. So I'll have today and then Thursday, and I'm going to breeze through some highlights. So I have to leave out a lot of stuff. But you guys have all had intro physics, right? So you understand a little bit about gravity and Newtonian physics. Can I make that assumption? Somewhat. Okay. Well, just stop me if you don't understand something, and we'll go into more detail. So there are a lot of different orbits that satellites can have around the Earth, ranging from really tight low Earth orbits, like look at the shuttle, how tight in it is. It's in about a 350 kilometer orbit. You can have highly elliptical orbits that are still LEO, like this guy. You can have geostationary orbits. You can have orbits with incredibly high inclinations. And why do you think they're so different? What drives the sort of orbit that you would like to have for your mission? The job that it's got to do. That's exactly right. So really, whatever problem you're trying to solve or mission you have really defines the orbit that's required. So that's why we have a variety of different orbits that are conceivable. By the way, this material comes from two places. It corresponds to chapters 4 and 5 in your textbook, the Jerry Sellers Understanding Space, but it also pulls material from the new SMAD, which is the Space Mission and Engineering book, and you guys will become real familiar with it as you get to your upper level classes. In fact, it's about this thick, and actually Bob and I wrote a chapter in it, so it makes a good pillow. At least put it under your pillow at night and learn through osmosis that way.
You never absorb anything out of it, though.
You don't?
I've been trying.
Right. So anyway, it's a good reference, and some of this material, by the way, comes from that source. But in the next couple hours-ish, what I want to do is tell you about the COEs, the common orbital elements. I'll tell you a little bit about the nature of orbits sort of globally. They're all conic sections, and they come in two flavors, generically bound and unbound. We'll probably just briefly touch on the underlying physics because of the time constraints, but what I really want to focus on are the different types of orbits between LEOs, MEOs, GEOs, AEIOUOs. Tough audience here. Molnias and Lagrangian gravitational equipotential points. And then we'll look a little bit about how they are defined by Kepler's laws, and these things called Keplerian elements, or TLEs, two-line elements, are really important when you look at the ground track and ground operation end of things. So I'd like you to understand a little bit about what the TLEs mean, because you'll be dealing with them a lot to establish ground tracks and contact with the satellites. And if we have time, we can go into some other things like perturbation and decay. But the main things we want to talk about are the types of orbits. So what sets the type of orbit, the job that you want to do? But think about the importance of the orbital parameters. The answer that you gave is perfect. You know, the kind of job that you're trying to do really defines the orbit. But there are all these parameters that you have to think about when you're trying to define the specifics of the orbit, when you're trying to define the inclination, when you're trying to define the eccentricity of the orbit, the altitude. So when do you think you should start analyzing orbits? Well, even a little bit before that. When do you start building a satellite? After what? Well, okay. You got to define the mission first. That's right. So the main thing is to define the mission, and then the mission definition drives everything. It drives the decisions about the satellite bus, the architecture. It drives decisions about the orbit. So really, it's really the very beginning. When you develop a mission objective, and then you start looking at your system's requirements, that's essentially when you start looking at all of these things that drive or driven by the system's requirements. And they're the orbits, the bus requirements, all the supporting structure, the launch vehicle that you need. All of those things are driven essentially by the mission objective. So that has to really be done early on, because even a lot of the bus definitions will be affected by the orbit that you select. And again, the orbit's selected based on the job that you're trying to do. But think of all these things that you have to consider. The revisit time, you know, it's great to have the right orbit, but you don't have access to every ground station in the world. So you might have a limited number of ground stations that you have access to, and so that, you know, to get your data down or to get your commands up, you have to be visiting your ground stations, making contact with your ground stations periodically. So that's driven by the mission constraints. Well, how much data do you need to get down? What's the throughput that you need? How often do you need the data? The spacecraft only has, you know, a finite amount of onboard storage. So when it flies over your station, it's got to dump the data down. So all of these things figure in to the orbit. Other parameters you got to think about are the radiation environment, the power generation. You know, if you select certain orbits, you'll be in Earth eclipse a lot, and you don't have the opportunity to generate as much prime power. There are orbits where you kind of skirt along the terminator of the Earth, called sun-synchronous orbits, and those are fantastic because you're in sunlight essentially all the time. So lots of different ways to choose the orbits and to think about the effects. Launch costs. You know, it's a whole heck of a lot cheaper to get to LEO than to get to GEO, for example. It takes a lot more delta V, a lot more change in your velocity and therefore energy to get farther out. It takes a lot to circularize your orbit. So there are all these considerations you have to think about. So what I want to do is give you a little bit of a flavor of the orbital parameters today that go into these considerations. So I thought I'd start off with a quote from Johann Kepler here, who, you know, Keplerian elements, he helped define orbits of the planets, which really it's the same set of physics. Once you understand the orbits of co-orbital bodies, you can apply it to anything. You can apply it to satellites orbiting the Earth. You can apply it to planets orbiting the Sun. You can apply it to stars orbiting the nucleus of the Milky Way. You can apply it to galaxies undergoing gravitational encounters. You can apply it to any kind of co-orbital situation. Same set of physics, exactly. So Kepler wasn't really thinking about satellites. He was thinking about planets, but he laid the foundation for a lot of the physics of orbital mechanics. And you can imagine, you know, in the 1600s when he's talking to his colleagues, so you see the orbit of a planet is elliptical. And much like students I've worked with in the past, you're thinking, okay, what's an orbit? What's an ellipse? What's a planet? Okay, again, tough audience here. Really, I mean, how many cartoons can you find about orbital mechanics? Right? So what is an orbit? Well, in physics, it's really just a path that an object makes around another body when it's under the influence of some sort of centripetal force. And generally the centripetal force is gravity, but it doesn't have to be. You could imagine, having satellites flying in formation away from the gravitational field of the planet, and then they could maintain an orbit around a barycenter without gravity being the primary force involved in the centripetal motion. So really there are two kinds of orbits, and it really depends on where the CG is, the center of gravity. When you're talking about bodies that have roughly the same mass, the center of gravity, as in this applet here, you can see, might lie somewhere in between the two bodies. If you have one that has a ginormous mass compared to the other one, where might the center of mass, or CG, center of gravity, be for that particular system? It could be inside the large mass. That's exactly right. So if the CG is inside the large mass, it's really the same set of physics, but we have different terminology. So you could say that bodies are co-orbital. That's when the CG is outside of the bodies, or if the CG is inside of one massive body, you typically refer to as one body revolving around the other body. But regardless of the scenario, the basic physics is the same. The CG has to be somewhere in between, a barycenter somewhere in between. Whether or not it's inside of one or not, it's in between the two. Okay, to understand orbits and the geometry and orientation of orbits, it's important a little bit, I believe, for you guys to understand coordinate systems. And that's why we have the cool globes out here. And I'm going to talk a little bit about different coordinate systems and then reference systems that we use to define orbits, and then we'll move on to the orbital parameters. But typically, orbits for satellites in orbit around the Earth, not satellites in orbit around other bodies, like if they're on orbit around, if they're on trajectories to leave the gravitational well of the Earth and to go to other bodies, then you'll have a different set of coordinate systems based on the solar system, essentially. But if a satellite is in orbit, a primary orbit around the Earth, we typically use a geocentric or Earth-centered system. And the coordinates for the Earth-centric system really have three points of reference, or three lines of reference in a fundamental plane. And what do you think the fundamental plane is defined by there? The equator. So the fundamental plane is really just a projection of the Earth's equator out. On the sky, we also have an equivalent of this called the celestial equator. And the celestial equator is basically, imagine this fundamental plane of the equator being projected into space. And if you drew a line around in the sky where that fundamental plane would intersect with the celestial sphere, then that's the celestial equator. And if you look on your globe here, and please be careful with these guys, they're about $500 a piece, believe it or not, but they're fun to play with. So the celestial equator is the central line here that goes around, again, projecting the Earth's equator into space. But you have the three geocentric coordinates. You have I, J, and K, and I is the one really that defines everything. So I is in the direction of the vernal equinox. Now, you're going to see the vernal equinox as a point of origin in geocentric coordinates and also in celestial coordinates. Well, what the heck is the vernal equinox? Anybody know? It probably means something to you already, but it might not mean really, that definition that you are familiar with might not be the one that you find to be relevant. Vernal equinox. Spring equinox. Equinox. Yeah. Okay. Yeah. So you have there are four astronomically significant days during the year, right? You have the solstices, which is the longest, winter solstice, longest night, shortest day. Summer solstice, the opposite, and then the two equinoxes, the fall equinox and spring equinox, where you have equal day, 12 hours, equal night. So everybody knows, when does the equinox fall, the spring equinox-ish? March 21st, right? About, okay. That's a practical definition. Really, there is another definition, which is really what the geocentric coordinate system is based on. And it turns out that there are two sort of fundamental planes on the celestial sphere. And we've already talked about the celestial equator here. So everybody, if you can work with a partner, grab that globe over there so you guys can sort of get a little experience with it. And if you look at the celestial sphere and see the celestial equator, there's another line, and the other line is called the ecliptic plane. And if you can't find it, because the globe's kind of busy, it has the bright stars on it, but if you rotate this little knob around, you can see that it makes a path across the sky, and that apparent path of the sun across the sky, this is the sun orbiting the Earth, right? Everybody still paying attention? Well, yeah. So it's the sun, but it's not really orbiting the Earth, right? So if you look at the sun throughout the year, it apparently orbits the Earth, but of course, you know, the Earth is orbiting the sun. But anyway, if you crank that sun dial throughout an entire year, you can see that it makes a path across the sky. And if you look really close to that path, you'll see the dates on it, right? Okay? Okay, put the sun on March 21st. So find March 21st. Excuse me.
Up a little bit to the left.
There you go. You're getting close now. Everybody on March 21st? Nope. Okay, you know what it might help is to sort of look through from the other side and see the dates. April. Yeah, you're pretty. It's got to be either here, that's September, so it's got to be over here. So do you see March down there? Okay, so crank your globe until I can kind of see from a distance who's close and who's not close. Okay, very good. Yeah. Yes, very good. Okay, now what do you notice about the position of the sun on the sky then? It's crossing the equator. That's exactly right. So, okay, so there are two planes of reference in the celestial coordinate system. There's the equatorial plane, again, the Earth's equator projected out into space, which is part of the geocentric. It's the frame of reference for the geocentric coordinate system. And then you have this other plane called the plane of the ecliptic. And as you move the sun around, it defines the plane of the ecliptic. There's a more practical way to think about what the ecliptic plane means. Let me see if I can explain that for a second. If I look at the solar system, if I look at the realm of the planets in the solar system, and if I look at how they're distributed in space, is the solar system, in terms of the realm of the planets, is it sort of spherical like a ball, or is it flat like a pancake? Flat like a pancake. It's darn flat, really flat. If you consider the major planets, it's incredibly flat. And there are reasons from stellar evolution that we expect it to be. But for our purposes here, so you could think of the ecliptic plane as the two-dimensional plane that the Earth and Sun live in. So let me see if I can draw you a little picture here. So if this is the Sun and this is the Earth, there's a plane that they both occupy, a reference plane, and that's the ecliptic. So if I'm talking about planets' orbits, I would measure the inclination or tilt of the planet's plane of its orbit relative to this plane. Like if I looked at Mars, for example, it might be a little bit above or a little bit below the ecliptic, but I would measure its inclination relative to that plane. Okay, so the first point in Aries that's defined by the coordinate I there is where the ecliptic plane and the celestial equator intersect as the sun's moving south to north on the sky. Okay, so it is the point of origin for various celestial coordinate systems and for geocentric coordinate systems. So to have a coordinate system, you have to have a plane of reference, right? In this case, the celestial equator, and a point of reference, in which case is 0, 0, is the first point in Aries or the vernal equinox. Okay, so everybody still on the vernal equinox there?
We're on the other one.
Okay, you're on the September. So go back to the vernal equinox, make sure everybody's there for a minute. Okay, so that's how you know what this direction is for the primary coordinate I. K is orthogonal to I in the direction of north, right? And then J is 90 degrees from there. So basically think of an orthogonal, you guys are familiar with orthogonal geometries, it's just a three-dimensional 90-degree angle, right? Like the corner of a box, right? So I pointing to the vernal equinox, K pointing to north, perpendicular to I, and then J is 90 degrees from I. So those are the geocentric coordinates. Okay, so now let's expand that out a little bit and move it to celestial coordinates, because you'll need to know these when we talk about how to track your satellites on the sky, how to find your satellites. If you want to impress a date, here's how you can do it. Because really, you know, if you can't impress a date, what are you really trying to learn here, right? So here's how to impress a date. You can go to, let's see, one of the sites that give you satellite trajectories, like spacetrack.org, or there's another one, Celestial, what is it, does anybody know? Where you can look up the path of the International Space Station. You can do that, right? And it'll tell you to look up at a certain time, at a certain azimuth and elevation, and boom, you'll see the International Space Station. So here's how you can impress a date. Go out and figure out when you're going to have date night, right? And figure out when the International Space Station is going to be at a certain set of coordinates at a certain time, and then you're just walking outside and walking around, and then you can say, like 2 minutes before, like, look up into this exact direction, and in 3, 2, 1, boom. And if you've ever seen a bright satellite, or particularly the International Space Station, it looks like they're satellites called the Iridium satellites, look like explosions on the sky. It is really cool. And then your date would be really, really impressed, I think.
It just passed you over with the same luminosity as Venus.
Yeah, so that's like -3. I mean, that's scary bright.
Yeah, it was cool.
It's crazy bright. And you can know exactly where to look for it. Well, it's the same thing when I'm pointing my big dish to a satellite and I need to pull down data or give a command, an uplink command. I got to know, where to point it, or I have to know what the ground track is, right? So this is what we're building up to. But to understand the two-line elements, you need to understand a little bit about the coordinate systems. Okay, so there are two celestial coordinate systems. There's the horizon system and there's the equator system. And they have two different points of origin and two different planes of reference. In the case of the horizon system, it's basically your local horizon. And if you look on your globe, the local horizon is the little blue plate there. And what you can do is kind of set it for the United States. So what is our, so here's the horizon at the equator, right? So if I imagine I'm a little person standing on the equator, I could look out in all directions and see the horizon. What would this be the horizon for? What latitude? If I'm standing here looking all around, I can see the horizon, right? So that's the horizon for the North Pole, right? So this is the horizon set for the equator. What latitude is Moorhead? A little lower. That's Stockholm. 38. Yeah, so 38. So if I want to set the latitude of Moorhead, just eyeball it, call it 45. That's close enough. That's a little north, but so that gives you an idea of what the latitude would be here. Okay, so go ahead and set your horizon for 45 degrees to represent Moorhead, and make sure your sun is at the vernal equinox. Okay. All right, sometimes they get a little twisted around, so let me fix you there. Okay, very good. Make sure your north arrow is pointing north. Yep, okay, this one got twisted. See the United States there? Yep. Okay. Let's see. I think we got to flip it over like that and then twist it a little bit. Sometimes these guys get uncalibrated, so we'll fix them. There we go. Okay. Okay. Let's see how we guys are doing back here. So find the United States, and make sure. Yep, there we go. Okay. And look at this one. Yeah. Yeah, but I want to set the horizon for 45 degrees latitude. There we go. Okay. All right. Now, so everybody's oriented. So there's this thing called the local meridian, which is the hour angle, or basically this great line that goes directly overhead. So if you're standing at the center in Kentucky looking up, the point directly overhead is called the zenith, right? And then there's a line that goes right through your zenith, pointing north and south, and it's called the local meridian, or the meridian, right? So what I want to do is have you guys put the sun on the local meridian, right? So just make sure it's going directly overhead. And what you got to do is leave the sun on March 21st, right? So you got to rotate the Earth underneath. So make sure the sun is on March 21st. And rotate the Earth until the 0 hour angle, right? So what's the, if you look back on the celestial equator, you see these hour angles, 0, 1, 2, 3, 4. Okay, the hour angle at the vernal equinox is 0. So another way to say this is to put the 0 hour angle of right ascension on the local meridian. Okay, now let's see, but still we got to leave the Earth at, oh, I see. Yours got all kinds of twisted around, but we will fix it. Okay, perfect. Okay, those look good. So make sure, in other words, put the sun directly overhead of Kentucky. Okay? All right, so that's at sunset, right? So the 0 hour angle, which is here, you want to rotate the Earth until it's overhead. So I want to put it overhead, and I'll rotate the Earth until it's overhead. And I got to make it 45 degrees, and that looks just about right there. Okay? Okay. So everybody looks pretty good here. Okay. Okay, so now we've got a certain date and time. You guys are at sunset. Oh, let me just give you an idea of how this works. Give me just a second here. Okay, so put the sun on the date that you want, right? And then imagine the horizon. I've got it set to my latitude, right? Approximately 45 is easy. If I'm looking toward the east and the sun is on the horizon, what time of day is that? Oh, sorry. Yeah, that's east. That's morning, right? Okay, so that's sunrise. And as I move through the day, when the sun's the highest it's going to be in the sky, what time of day is that? Noon, okay? And then if the sun's setting in the west over here, sunset, okay? And if the sun is at nadir, you guys know what nadir is? Opposite of zenith. What time of day is that? That's midnight. That's exactly right. Okay? So I can represent your horizon and the celestial sphere and the sun for a specific time of day. So if I put the 0 angle of right ascension, in other words, where the vernal equinox is directly overhead, or as high overhead as it's going to get during that day, then the time of day I have for this situation is what time? It's noon, exactly. Okay. So here's what I want to do. To illustrate how the horizon system works, you need 2 coordinates. So all celestial coordinate systems are just like geographic coordinates, where you have latitude and longitude. Longitude will tell you how far around you are, right? Latitude tells you how high up and down you are. In the horizon system, what tells me how far around I am is azimuth, the coordinate of azimuth, and it goes 0 to 360, right? So 0 is north, 90 is what? East, 180 is south, and west would be 270, right? Okay. And then the height above or below, the angle above or below the horizon, in this case the blue horizon plate, is my altitude. And I measure it in 0 to 90. So if the object's at zenith, that would be 90 degrees altitude. If it's at 0, then that would be 0 degrees altitude. Okay? So what I want you guys to do is estimate the azimuth and altitude of the sun at noon on the vernal equinox. Okay, let me make sure the horizon plate's working for everybody. Yep. Make sure we got it oriented right. Are the numbers on the top of the horizon plate? Yep. Okay. Okay. So altitude's easiest to do, right? So I got to eyeball. You just eyeball it. Nor if we were going to do this the right way, we would take, some string and calibrate it with the hour circles. But just for the point of illustration, just to conceptually understand the coordinate systems, want to have you guys give some estimates. So, what do you think the altitude of the sun is in that situation there? 45? Yeah. It's pretty close, isn't it? Yeah, maybe a little less. Let's see. Okay, so you got to set the horizon, and then you got to get back to the vernal equinox. Right over here, put your sun. Is this March? No, that's September. You were right. You were going to the right place. Now, put your sun directly overhead, or the sun. Okay. So let me show you. So it's this angle that I'm trying to measure here above the horizon. So imagine you're a little person sitting on the horizon, on the Earth in Kentucky, and the angle above that blue horizon plate, if this is 90 degrees and this is 0, the angle of the sun above the horizon is about 45 degrees, exactly. So what's the angle above the sun and the horizon here? 0. So here, about 45. What would you call this? 10 or 20, yeah, absolutely. Okay. So altitude, you can think of it as the angle or height above the horizon. Okay. Oh, let me give you one more. What's the altitude of the sun here? There you go. Negative 10-ish. Okay? Okay, so that is the altitude. The azimuth is a little bit trickier. All you got to do is imagine dropping the perpendicular line down to the horizon plate, and then you can read the azimuth. Azimuth, again, tells you how far around on the sky. So if I'm looking at north, that's 0. Again, east would be 90, south 180. So what is the azimuth of the sun at noon on the vernal equinox? Find out where it's perpendicular and it drops straight down. And then read the azimuth from the horizon plate there. Here's a conceptual way to think about it. Imagine standing in Kentucky. There, what direction would I have to look to see the sun? Oh, the little pointy arrow is north. Yeah, it's due south or 180 degrees. So if I want to tell you where the sun is in this scenario at noon on the vernal equinox, I would have to give you two coordinates. I would give you an azimuth and an altitude. So the azimuth would be 180 and the altitude would be 45. Okay. So if I gave you coordinates, you could go out and find anything, right? So when you look up on Celeste track and figure out where the International Space Station is going to be, it'll say at 10 o'clock at night, it's going to be at azimuth 260 and elevation 30 degrees. You just take a compass and figure out where north is. Take your cell phone, figure out where north is. Swing around 270 degrees. That would be west-ish. And look up 30 degrees above the sky, and boom, that's where it is. So coordinates, azimuth, and elevation. Questions about this? Is this something you guys already knew about? Okay. All right. Pretty simple, though, right? Once you sort of orienting the globe's complicated, but once you get it oriented, trying to figure out, the coordinate system's not too bad. Okay, yeah. Oh, it's past time. Sorry. Doggone it. Okay, we will continue. Okay. Okay, fantastic. So we'll continue on Thursday then. Thank you guys.